Okay. Many thanks, Chandra, and all the organizers for inviting me here. Today, I wanted to start talking about numerical relativity. Numerical relativity is a subfield of, at the intersection of GR applied to astrophysical problems. And it is often thought of as a very mixed field, very applied field, where you take concepts in applied mathematics, numerical methods, computer science, and you apply all of them together to solving complicated dynamical problems in full nonlinear general relativity. Okay, so in this lecture, I hope to get you all started with the basic formalism that lies underneath this field, and how we get there and how we actually apply it to real problems. So in brackets here is the context of what I'll be talking about. I'll be limiting myself to applications that are relevant to gravitational wave astronomy, which is, since the last decade, has become an observational subfield of astronomy, where we have started regularly observing gravitational waves from highly dynamical compact object binary systems of black holes and neutron stars, or black holes and neutron stars, colliding into each other. As these highly compact systems do in spiral and coalesce with each other, they change the very nature of space-time around them in a time-dependent fashion, and this change propagates outwards from the system in the form of gravitational waves. And to us, to the observers, by us I will mean the two observatories or the three observatories that we have in operation at the moment. The LIGO observatories have been shown here. They are located both in the North American continent at Hanford and Livingston. And they are oriented exactly as shown in these pictures at 45-degree angle to each other, or by design, so they are sensitive to different polarization content of the gravitational wave signal that is incident upon this face of Earth. Okay, so right. I think Sumanta or others may, or Shashwat may talk about the observatories in more detail, but effectively these are Michelson interferometers. And what they measure is difference in length between two fixed points, that between two fixed points here as well as two separate fixed points here, and how these differences in the distance between the two pairs of points changes as a function of time. Okay, and the net difference is what is measured here at the differential arm, as the differential arm output, and this constitutes what is called the strain signal. That is the final observable that has been in the news, and you must have seen various time domain plots of these gravitational wave strain signals. Okay, so this animation will show actual results from numerical relativity simulations. So what is shown here are I think around 35 events from the first, second, and the first half of third observing run of LIGO-Virgo detectors. What are shown here are the two horizons that will inspiral as well as merge within the span of this movie here. These are all coming from our numerical relativity simulations. Probably don't need the sound, so let's shut it off, but you can see the time scales of different systems are different. The lighter systems, they will coalesce in much longer time, and the heavier systems will coalesce much more quickly, and we'll discuss why that is. Okay, so this figure here summarizes some of the prominent events from the first two observing runs and the measurements that we could make from the gravitational wave signal about the masses of the two black holes that actually coalesced to produce those particular signals. So you will see, for example, some of the lowest mass events have their masses being constrained to these banana-shaped contours here, while some of the heaviest events have masses that are contained in this region, that is, for example, given as a purple contour here. So we have seen black hole collisions with individual compact object masses going from a single digit solar masses to 50 solar masses and so. which are coalescing to form say 100 and 100 plus solar mass black holes, and we are now in the territory of seeing the formation of intermediate mass black holes in real time through these events. Okay? So why is the mass of the system more important? Is important in this. So remember, in GR, the total mass of a given system can be scaled out, which means when we insert back units by imposing the sensitivity curves of our instruments, what happens is that heavier systems, they actually emit at lower frequencies, and the lighter systems emit at higher frequencies. So for the heaviest events, it is the very late part of the in spiral as well as the merging down process that happens after that is very brightly visible in our ground based detectors. Okay, and this is where exactly numerical relativity will play a part. If all our systems, all our sources were very low mass events, say BNS events and so on, all we would see is very early in spiral for these signals, and very early in spirals can be captured reasonably well using perturbative techniques like post-Newtonian theory and allied formalisms. But if we are to see the very merger of these objects, we have to be able to solve Einstein's equations in their full nonlinearity, right? So for example, the heaviest system that I'm showing here amongst these three has the shortest pre-merger part visible to LIGO detectors, and as you decrease the binary mass, the amount of in spiral increases that is visible to you. Okay, so what is the role of numerical relativity in this field of gravitational wave astronomy, right? So here is briefly a flow chart of how this field of astronomy is actually currently operational. We have sources, compact binary sources primarily, which emit gravitational waves. We have detectors which actually measure those waves, and out comes the strain time series, which is then passed through a set of calibration routines which tell us, which change what the raw detector output is into calibrated strain data, which we can actually use to match with our GR based waveforms and reverse engineer what the sources must have looked like. So with this strain data, the discovery process begins. Now the problem is that this strain data is entirely noise dominated. These signals are incredibly small. They have to be really dug out of the noise to make sense of them. And that is where the following stages enter. So the first stage is that of match filtering, where we take a large set of what we expect these waveforms or signals to look like. We call them a bank of waveform templates which are based in GR, and we filter all of the data coming out with each of these templates here. And after that, what we find is there are many pure noise coincidences between our templates and the data is coming out. We have to rule them out, and once we have ruled out all of those, what is left over is most likely a real gravitational wave signal. So in order to understand if a signal is coming from noise or it's a real astrophysical signal, we go through the second stage, where we not only do an fully integrated test of consistency with GR, we also do a instantaneous. So in this block here, what we are looking for is a full integral match between the entire signal over the entire frequency range and the actual and the predicted templates. But in the second stage, we make the frequency evolution of the observed signal actually expect from GR. Okay, so typically the output of these two stages would look like this. We'll have hundreds of thousands to even millions of noise triggers and some gravitational wave events that will stand out prominently against this background of noise triggers. And finally, once we have identified a signal, we do detailed parameter estimation of this signal by comparing against GR waveforms in a lot more detail using a Bayesian framework. And this allows us to uncover the masses and spins of the black holes that actually gave rise to these signals that we see. So as you can see, these waveforms are central to the entire starting from match filtering, signal consistency, as well as Bayesian parameter estimation. And this is where waveform models come into the picture. Okay? So we need waveform models that are able to predict what these sources' emission in gravitational wave spectrum would look like. And this is where numerical relativity actually enters this whole field. Okay. So now again, I have already spoken about LIGO's waveform needs in terms of signal detection, in terms of parameter estimation. For example, okay, for example, this figure shows the measured masses for the very first GW150914 event. And it's important to highlight that both of the waveform models that were used to measure these were calibrated to a lot of numerical relativity simulations to make them accurate enough to analyze this event. Okay? And finally, the third important aspect is being able to test GR using these gravitational wave signals that give us a unique window into very dynamical, very strong field gravity. And here also we need very high precision waveforms, especially waveforms that capture the near merger as well as the post merger process of the two body system. Okay, so for example, without using numerical relativity information, many of the very first events and even events that we are observing currently would have had much lower significance. In fact, the first event would have had maybe instead of a 5 sigma significance would have been detected with approximately 2.5 sigma significance, which would not have merited a confident detection for that. And most importantly, this figure is actually to be understood. What is shown here is the measurement of the post-merger black hole's mass and its angular momentum or spin. And if we use only information from, say, perturbative post-Newtonian waveforms, what we measure is this contour right here. And if we, take only the post-merger waveform that can be calculated using black hole perturbation theory, we measure the two observables to this much precision. Whereas if we combine the two as well as use information from numerical relativity, we can get a much more precise measurement of the final black hole's condition. Okay, so that sort of sets the context of the problem, right? And over time, numerical relativity has become more important because 20 years ago, the expectation in literature or in the community was that what we will see will be neutron star mergers, a large population of those mergers with a few black hole mergers thrown in for fun. But it turns out to be quite the opposite. What we are seeing is a large number of binary black hole mergers, and the rate of their observation is increasing with time as the instrument sensitivity increases continuously, right? Okay. So what are we doing here? What we are doing is we are trying to simulate binary black hole coalescence in full nonlinear GR as an application of numerical relativity, right? So in Newtonian gravity, I mean, the equations are much simpler. In Einsteinian gravity, you have you replace the role of gravity from being a force to determining the geometry of the space-time fabric itself. The geometry can be contained into a rank 2 metric tensor, which is determined by solving Einstein's equations at all points in space-time, right? Now, the very first attempts to solve this problem in full numerically was made as early as 1964 when Susan Hahn and Richard Lindquist used some of the early IBM computers to try to evolve Einstein's equations in a particular formulation. And they were actually able to do it for I think 50 time steps, that's right. But at which point the simulations crashed because of numerical errors, and we'll discuss why exactly that was happening. And this problem plagued the field for 40 more years from 1964, right, until about 2005, when the first stable evolutions of binary black hole spacetimes was produced by Franz Pretorius at Caltech. Okay, so this figure shows the trajectory of the two black holes from this simulation, and this shows the psi4 being emitted as a function of coordinate time. Okay. So soon thereafter, because the field itself had matured, several groups around the globe used different methodologies and different numerical schemes, for example, to solve the same problem. Okay. So let's get started on trying to understand how we go about this business. Okay. So we have our Einstein's equations here. So we have the Einstein tensor, which is a full space-time four-dimensional rank 2 tensor, which can be written as the Ricci tensor with this trace subtracted out, and this is equated or sourced by the stress energy tensor, which is given by matter and other fields in the system. Or in the case of binary black holes, this right hand side will be identically 0 except at the singularity. Okay. So these are of course symmetric tensors. So this correspond to sort of 10 partial differential equations. 6 of them are second order quasi hyperbolic partial differential equations, which tell you how space-time curvature evolves in time, and 4 are second order elliptic partial differential equations, which constrain the behavior of curvature related quantities within instantaneously. Okay, and we'll see how to actually derive these starting from Einstein's equations as we go along. Okay, so the moment we try to solve Einstein's equations, we come upon an immediate conceptual block, which is that in GR, GR states that our world is a full 4D curved space-time, right? And Einstein's equations treat time on the same footing as any other spatial coordinate, right? Which is of course very elegant conceptually, but it is a problem when we are trying to solve these equations numerically. There is no a priori concept of the flowing of time in some senses. So if, for example, we try to solve Einstein's equations in the full 4-dimensional version, what we will have in front of us are fully elliptic partial differential equations. And to solve elliptic partial differential equations, you need boundary data for your system, which in this case would require boundary data for the full 4D space-time, right? Which also includes at a boundary of time coordinate itself, which of course we will not be able to provide. Therefore, that direction is entirely futile. So what do we do? There is a successful recipe for actually making meaningful progress. So we, and by we I mean our observatories, our instruments, and of course us humans, we have the illusion that we live in 3-dimensional spatial slices of this 4-dimensional space-time, right? And so it is easier for us to tell or use computers to perform simulations that progress from a given time to the next time step, to the next time step, and so on and so forth, as we are able to provide initial data on a given spatial slice, as well as boundary data at the boundary of our spatial slices. So given these constraints, we have to find a way to somehow split space-time manifestly into space and a single time-like coordinate. So given a manifold, a 4-dimensional manifold, we start with introducing a scalar field which we denote as the time coordinate, and the restriction on that scalar field has to be that level sets of that field make up space-like hypersurfaces, in 3-dimensional space-like hypersurfaces in the 4-dimensional space-time. Okay? So once we have designed that, what we have is some spatial hypersurfaces which are 3D, which are level sets of time, say a value of t0, and an entirely non-intersecting separate level set sigma 2, which is separated from the first one with a small difference in the value of the time coordinate. Okay? So given this initial definition of the scalar field, what we can now induce is a direction of time by taking a covariant derivative of the scalar field. And this gives us the direction in which time is moving forward, right? So note that you are free to specify the scalar field however you like, for example, with the basic requirements that I have stated. Now we can normalize this scalar field by computing the norm of, normalize the gradient by computing the norm, and we assign it we assign a special name to it, and this name is called the lapse function. This lapse function is strictly positive if these hypersurfaces are actually space-like at all time, space-like. And lapse function has to do with how the relative rate of coordinate time movement and proper time movement. How much does proper time move forward as our coordinate time is moving forward. Okay, and that's the information content in lapse function. Now, given this direction of time and a normalization, we can write down a unit normal vector, which is written as this: lapse function times 4D spacetime metric, and then the gradient of the time scale field. And because of the signature that we use, the norm of this vector will have to be -1. Now, the spatial metric is given as effectively the 4D spacetime metric projected onto these 3D slices. So this plus normal plotted together will give us the spatial metric that actually gives the proper distances between 2 points separated to any 2 points in the same space-like hypersurface. Okay. And we can also define a general time vector. So imagine a coordinate observer, an observer which is sitting at a fixed coordinate location, such that so say for example it's sitting at the origin of your spatial coordinate system, and it doesn't move from the coordinate origin, right? So the flow of this observer's time will be tangent, the tangent to that flow is what we will define as the time vector here, right? And this time vector, when projected along the normal, unit normal, will actually give us the lapse function. But this may also have a non-zero projection along the space-like hypersurfaces, and this gives us the shift vector. And what does this shift vector mean? This comes from the fact that even though the coordinate observer is sitting at the origin, you may be moving the origin around. You may be specifying some time-dependent spatial coordinate system, in which the coordinates themselves move with respect to the space-like hypersurface, and that movement is captured by this shift vector. Okay. Okay. So a simple example would be, for example, a rotating coordinate system. Suppose you were solving the two-body problem in a rotating coordinate system that is rotating in a way to emulate the actual orbital rotation of the two-body system, right? So if from one time step to the next time step to the next time step, your actual coordinate system is has moved in the angular direction, right? And so the shift vector will have a non-zero angular component in that coordinate system. Okay. Excellent. So the first in solving Einstein's equations was to induce this split, which we have been able to do. The second step is, of course, take all the 4D tensors in Einstein's equations and write them in terms of their three-dimensional counterparts, as well as, of course, the normal vector here, right? So by using this normal vector and the spatial metric, we can actually decompose any 4D tensor into a purely spatial part by using the projection operator. That actually the spatial metric will act as a projection operator, right? So here's the spatial metric with one index raised, and this can be used to project any single rank 1 contravariant or covariant tensor into the space-like hypersurface that we will have, right? Where the time-like part of the same tensor can be projected, can be given by subtracting out the spatial projection from the original tensor, which is equivalent to projecting that tensor with this operator, right? And the two operators are, of course, expectedly orthogonal. Okay. So for example, the full 4D covariant derivative can be, if it is operating on a mixed covariant contravariant tensor, for example, as written here, can be used to get the 3D version of it by projecting all the three indices using the projection operator that we just introduced. So using this, all the 4D tensors Einstein's equation can be projected onto the spatial slices. and the Christoffel symbols, the 3D Christoffel symbols have the same familiar form as they do in 4D, except now you replace the space-time metric with the spatial metric. And so does the 3D Riemann tensor as well as the Ricci tensor and the induced scalar. Okay. So in my right, going forward, in equations where we have mixed 3D and 4D tensors, I will write subscript 4 or subscript 3 to distinguish between them. Otherwise, whether it's a 3D or 4D tensor, it should become clear from the equation. Please feel free to ask questions and so on. Okay. So now, the information that is present in the 4-dimensional Riemann tensor, which gets removed once we get the spatial projected version of it, is actually what is the information contained in the quantity called the extrinsic tensor, extrinsic curvature. So, extrinsic curvature can be defined as the following. So, it can be defined as the spatial projection of the covariant derivative of the normal vector, right? And this is an important geometric concept. So, this quantity tells us how your spatial slices are curved as they are embedded in the higher dimensional space-time itself. Okay? And in fact, it can be shown that the extrinsic curvature is related to the Lie derivative of the spatial metric along the unit normal that we had just introduced earlier. So, this expresses the fact that this extrinsic curvature can be seen as the rate of change of the spatial metric along the normal vector. And the above, I think, expresses this geometric picture in tensorial terms. So, for example, if you have the local normal of on your spatial slice, which gets parallel transported to a nearby point here, then most likely, at least if the slice is not flat, this will no longer be the normal at this point, and the difference between the actual normal and the parallel transported normal is what is described by this extrinsic curvature tensor. Okay, so if you had a flat slice, then the two normals here, the two vectors here will coincide, and k will be identically 0, for example, right? Okay, so we have split space-time. We know how to project things along the time direction as well as the space direction. Now, step 3, we decompose Einstein's equations and we write down the Einstein's equations in a 3+1 form. So, to do so, it is important to note these 3 equations, 2 of which are written here. And I won't derive them, but some of the equations that I will talk about here will be part of the tutorial in the afternoon. So, first is the Gauss-Kodazzi set of equations, which are obtained when you take the full 4-dimensional Riemann and you project all the indices onto the spatial slice, right? And you see how nicely all of this information is contained in the 3D Riemann as well as the extrinsic curvature, which is consistent with the geometric description I gave a little while ago. Okay? Now, instead of projecting all of them onto the spatial slice, if I only project 3 of the indices and project 1 along the time-like direction, I am bound to introduce some derivatives on the left-hand side, which is exactly what we find. So, this particular projection is related to the derivatives of the extrinsic curvature here. These form the Kodazzi-Mainardi equations. Now, the third equations, they are the Ricci equations, which are given by taking 2 spatial projections and 2 time-like projections, and they can be written in terms of the Lie derivative of extrinsic curvature as well as the 3D covariant derivatives of the lapse function and the extrinsic curvature here, right? So, this equation will be important later because hidden inside this is the seed of the time evolution equation for the extrinsic curvature. Okay. So, now we also can do similar projections on the right hand sides of Einstein's equations. For an Eulerian observer, the rest mass density can be given by projecting the stress energy tensor along the time-like direction twice. and along the time-like direction once, and along the spatial hypersurface once, to give the momentum density again measured by the Eulerian. This is just notation that we will use later on. Okay, so now we can actually go and do these projections in and derive the equations that will govern the evolution of Einstein's equations. Okay, so remember I described that Einstein's equations get split into two distinct set of equations. One is constraint equations, which are fully defined on the spatial hypersurface itself. They have nothing to do with the next or the previous hypersurface, spatial slice, right? They constrain how the geometry of that slice should be. And evolution equations relate how the geometry would evolve as you move from one slice to the next, and so on and so forth. Okay, so if I'm losing some of you, feel free to stop me and ask questions about any of this. Good. So let's talk about how we get the constraint equations first. So now we can time project the Einstein's equations or Einstein's tensor and use Gauss-Kodadzi equation, which were these. So if we operate with the spatial projection operator twice on the Riemann tensor, we get this is equal to twice time projection of the Einstein tensor, right? And this quantity using Gauss-Kodadzi equations can be expressed to be equal to the following right hand side here by simply taking the twice of Gauss-Kodadzi equation. So here you take the trace twice, you get k squared and k dotted with k, which you have here. So this is the first important relation, which if you insert Einstein's equations back into it, the left hand side changes into the equivalent for the stress energy tensor here, and we get this is equal to 16 pi rho, giving the Hamiltonian constraint equations, which uses the Gauss-Kodadzi equation as well as Einstein's equations in its derivation, right? Okay. So similarly, if instead of two time projections, if we do one spatial and one time projection of Einstein's tensor, we can write it in this particular fashion, and again using Kodadzi-Mainardi equation, the second one, we can relate this with the derivatives of k, and this is the contracted version of Kodadzi-Mainardi equations. Remember, those equations had 4 indices. We have taken 2 indices away by contracting with the contravariant metric tensor. And relating this to the right hand side of Einstein's equations, we find the momentum constraint equations, right? So these are actually only 3 equations. The 0th component of them is trivial. So we have 3 plus 1 in the previous slide, 4. These are the 4 constraint equations that the extrinsic curvature as well as its derivatives and spatial metric tensor must obey at all time slices. Okay. So these are actually necessary and sufficient integrability conditions for embedding these slices back into the 4D spacetime, for the slices to be compatible with the original 4D spacetime to begin with. Okay, so now the evolution equation. So the first evolution equation actually comes from the relation where we derive, which we talked about earlier, which is given by the extrinsic curvature being equal to -½ Lie derivative of the spatial metric tensor along the normal direction. Now I am multiplying the normal vector with the Laplace function here, and then expressing the Lie derivative as a sum of Lie derivative along the time vector minus the Lie derivative along the shift vector, right? Because if you remember, the time vector was defined as this. So I am able to write this down. And that is why that relation had the seed of the first evolution equations. So I will replace the Lie derivative of the normal with these two to write down the first evolution equation for the spatial metric tensor itself. Okay. Notice in this derivation though, I have not used Einstein's equations. So this is a purely kinematic equation. This does not affect or evolve the dynamics of the systems. Okay. And if I expand the Lie derivative, I can write down in the familiar form using partial derivatives alone. Okay, good. And then we have the final set of evolution equations which must tell us how the extrinsic curvature evolves itself, right? And the starting point of this is the Ricci equation which I had shown earlier, where the Lie derivative of the extrinsic curvature was related to the 4D Riemann as well as derivatives of Laps and extrinsic curvature, right? So if you remember, just go back very quickly here, this equation. Now we'll do the same trick. We'll replace the normal vector with time t minus beta, time vector minus beta, right? Here. So I replace this with t minus beta. So this is how I get, for example, this is the Lie derivative in beta, this is the Lie derivative along time, and I express this projection of the 4-dimensional Riemann using the Gauss-Kodazzi relation in terms of the Ricci and extrinsic tensors, right? Second term, which is not very visible for some reason, okay, actually expands to this bracket over here without the 2. The second identical term is coming from this term right here. Okay, you might be wondering there was no 2 in the sorry, this equation, for example. This is the one I have applied there. Okay. So this gives us the second set of evolution equations that tell us how the spatial or the extrinsic curvature of our spatial slices evolves as we go forward in time. Okay. So now we have written the equations we need are complete in some sense, right? We have extracted all the content of Einstein's equations in terms of these 4 tensor equations, right? One Hamiltonian constraint equation, one momentum constraint, and 2 evolution equations for spatial metric and extrinsic curvature. Okay. Now we can now specify a coordinate basis, and we can specify a coordinate basis that is naturally adept to the coordinates that we are using. So, you know, for the spatial vectors, unit vectors, we have this, and for the time-like vector, we can define this as the basis vector, which reduces the Lie derivative along time or as the partial derivative. And putting it all together, what we get is the following single slide. This single slide summarizes most of the quantities that I have discussed so far. Okay, so this is the full 4D metric written in terms of the 3D metric and shift as well as Laps functions expanded out right here. Just going to pause here for 2 seconds to see if people have questions about this. Okay, how am I doing on time? Half an hour. Good. Okay, so either, yes. Here.
Yeah. So when you expand out the second equality, what happens to the this metric?
When you expand out the second equality,
So you are basically projecting the covariant derivative using the extrinsic curvature.
covariant derivative of the normal vector projected onto the spatial slice. So this is telling us how the normal vector is so this covariant derivative will tell us how the normal vector is changing along all 4 dimensions. I only am interested in how it is changing along my slice, hence the projection. So also interesting thing to note that this covariant derivative is not symmetric, whereas after you project it on the slice, it does become symmetric. So the non-symmetric part of this derivative has to do with the Laps function or how it changes with time. But when you project it back onto your spatial slice, it becomes symmetric in the 2 indices. Okay. So in fact, in one of the tutorial problems in the afternoon, you'll be working on how we came about this magic relation, which tells us how the metric of the spatial slice evolves in time. Okay. So now summary of the idea that we have. So this is usually called the ADM form, Arnold Deser Misner form. In fact, that's sort of a misnomer. These equations that we have described and are commonly used are a rewrite due to York of the original ADM equations. Original ADM equations actually don't use this extrinsic curvature, they use the momentum variable conjugate to the spatial metric in the Hamiltonian form of GR. So original ADM equations and the ones that I have described here, they differ by addition of a multiple of the constraint equations to the evolution equation, right? Anyway, so we have decomposed, we have first split space-time, we have decomposed tensors along the normal as well as along the spatial slices. We have rewritten Einstein's equations using two special functions that tell us how our coordinate degrees of freedom evolve and change, and then we have allowed for a basis and expressed all these equations in that basis. Okay. So now an important thing to note here is the choice of your lapse and shift functions can determine how well posed or how, what is the mathematical nature of the final 3+1 evolution equations. Are they strongly hyperbolic, are they weakly hyperbolic, and so on and so forth. So what we want is for them to be strongly hyperbolic, and that would mean that they have they have unique solution as you evolve those equations forward in time, and any small changes to initial data only leads to small changes in the evolved variables after a finite amount of time, okay, which is absolutely a requirement if we want to have stable numerical evolutions of these systems, because small deviations of initial data will happen because of numerical errors, if nothing else. So analytically, ADM equations, they guarantee if you start with initial data which satisfies Einstein's constraints, then Einstein constraints will be satisfied forever. But numerically, that is only going to be true up to some round off error in the initial data. And we will have to change, we will have to sort of use a particular form of these evolution equations that will allow for a damping of any small violations of constraint equations that may happen. And this is a point I will bring up later. Okay, so necessary condition, for example, is strong hyperbolicity. The ADM equations I have described are only weakly hyperbolic, which means that while they have distinct characteristic fields, some of them actually propagate at the same speed, which can cause some mixing in their numerical representations, and that effectively leads to small changes in initial data, giving large changes after a finite amount of evolution time. Okay, so that is why these ADM equations are almost not used in the form that we have been writing them to do numerical evolutions. They are suitably changed to actually do stable evolutions and so on. And the knobs that we have available to us to change the nature of these equations are the gauge degrees of freedom, which can be understood as the choice of the lapse and shift vectors. Right. Okay. Yeah.
So these divergences that appear to that you mentioned, are those like numerical artifacts because of limited precision of the machine, or do they arise from the behavior of the field?
Right. So there are two things here. So if you have, for example, weakly hyperbolic systems, they will still satisfy this inequality that the solution after some time in the future should not exponentially grow beyond what the initial state was. Yes. So in that sense, even weakly hyperbolic formulations should be good enough. Okay. Strongly hyperbolic are more stable. Now, what I was talking about earlier are numerical perturbations or errors in the initial data growing also exponentially to give large deviations in phi of t. So there are, at the analytical level, weakly hyperbolic is fine, but at a numerical level, we want a strongly hyperbolic formulation. Okay, so let's talk very quickly about another formulation of Einstein's equations that we actually use in practice. So we, by when I say we, I mean the group called the Simulating Extreme Spacetimes Collaboration, which has developed a code called Spectral Einstein code, and this uses a formulation called the generalized harmonic formulation of Einstein's equation. This is also a first order formulation, but it's derived slightly differently. So we start with this particular form of expressing the Ricci curvature tensor, right? And you see that this being equal to 0 gives you the Einstein's equations. Now the second derivatives in this are contained only in this first term as well as the second term, right? If we somehow get rid of the second derivatives in this term here, then the equation will, this equal to 0, will become a manifestly hyperbolic, manifestly wave-like equation, right? Because we have the wave operator and some source terms over here, and that only include the first derivatives. So how can we get rid of the second derivatives over here? Is by using our gauge degrees of freedom, right? So what we do is we set these Christoffel single index Christoffels to some source functions which we design for the problem at hand. The only restriction on them is that they should not contain any derivatives of the metric to begin with, otherwise the point is lost, right? So we define these source functions, we replace gamma with some source function h, and this now fixes our gauge. This is equivalent to fixing the lapse and shift degrees of freedom, and we make sure that this has one order of derivatives lesser than the original gamma that they are replacing. Okay, so this becomes the form that we wanted to get into, and this is a manifestly wave-like equation that we can solve. And as I said, this becomes then our gauge condition, which actually can be written in terms of the familiar lapse and shift functions in the form of the following two differential equations. This gauge condition corresponds to the following evolution equations for the lapse and shift functions. Okay. So now that's the generalized harmonic gauge. Then we reduce the order by introducing auxiliary variables. So we take the space-time metric and we define its spatial derivatives as free variables, as well as the time derivative also as a free variables, to write down Einstein's equations or the evolution equations in the following form. So this is the full generalized harmonic first order form that we actually evolve in practice. Okay, so this plus this and so on, and you can see the gauge condition is entering at some points here. Okay, so what makes it challenging to solve these equations? Why is it challenging to actually do this in practice? The first challenge comes from the fact that we have many length scales in our problem. We have length scales that are ranging from over, say, I think 3 orders of magnitude at least. The smallest length scale we have are the size of the horizon, black hole horizons that we must resolve, as well as the oscillations on those horizons that we must resolve at all times. Then the separation between the black holes is, or say, order 10m. The wavelength of gravitational waves being emitted is another order of magnitude larger length scale, as well as if we are solving the two-body problem, our domain must be large enough such that we are able to extract the waves at least a few wavelengths away or in some sort of a weak field region away from the source itself. So that is what gives a range of 3 to 4 orders of magnitude in terms of length scales. Now, we don't know which coordinates to use. For example, I have described the generalized harmonic formulation, but I have cleverly not told you anything about how we set h, the gauge source function, right? How do we set that gauge source function? For a space-time, we don't know in advance. When we are solving for the collision of two black holes, when the two black holes are in very close proximity, that's where things can become extremely nonlinear. It's very important to calibrate your source function very carefully for the problem specifically you have at hand. So finding this is an iterative process. Now, handling singularities on a grid is of course always fun because computers like infinities, of course, but we'll have a few, in literature there are two basically two ways of handling singularities, and I'll talk about them, at least one of them, in the next few minutes. Then the fourth problem, Einstein constraint equations. So now once we have written down the evolution equations, we have two choices. What we can do is we can solve the evolution equations to go from t to t plus dt, but for all degrees of freedom minus 4. And for the remaining 4 degrees of freedom, we can solve the Einstein constraint equations on the t plus dt slice. That would be called a constrained evolution, and that would be perfect. It would give us very nice convergent stable evolutions, except solving the constraint equations at every time step is very expensive. Solving elliptic partial differential equations is prohibitively expensive. So what the other alternative is to simply evolve the evolution equations and hope that Einstein constraint equations remain satisfied at all time slices. And this hope was what didn't quite work out for about 40 years. Those constraints were becoming exponentially non-zero in the original simulations of Susan Hahn and Richard Lindquist in 1964. This remained an outstanding problem for several decades, and this was actually the key missing bit that Franz Pretorius inserted into the whole machinery that we have described here. Okay, so it's important enough that I'll show you how to do this in practice. Computational challenges, we have many variables. In the second order formulation we had fewer, but in the first order formulation we have these many variables. So there's, just count the number of variables, you'll find around 50 degrees of freedom over here. So we are solving 50 hyperbolic PDEs in 50 variables, strongly coupled together, right? And finally, the high accuracy required by LIGO and other observatories mean that we need very good, very faithful phase evolution for a long duration of evolution. Okay, so we really need good ways of numerically stabilizing these simulations as we go along. And this is the thing about numerical relativity. It's only about 30% GR, 70% engineering, which comprises of using techniques from applied mathematics and all sorts of computer science subfields all together to solving this dynamical gravity systems and so on. Okay. So now some of these challenges can be alleviated when we are in vacuum, when the solutions are smooth, when we don't have, for example, fluids or stars colliding into each other, creating shocks and discontinuities. When we only have black holes, for example, solutions are smooth everywhere except at the singularities themselves. And for such systems, we can use spectral methods. So that's the sort of those are the numerical use in the spectral Einstein code, which was developed by the simulation of extreme spacetimes collaboration. The benefit of that is shown in this slide, for example. So when you have any field, in the spectral discretization scheme, you express that as a linear combination of some basis functions. These basis functions can be Chebyshev Legendre polynomials, they can be Fourier series, they can be spherical harmonics. The choice of these basis functions is actually very important to achieve good convergence. So if your final solution is expected to look like a Fourier series, you might as well use those instead of, and not polynomial basis functions, to ensure good convergence and so on. This expansion also separates the spatial and temporal dependencies in the original field to begin with, which means now anytime you want to take spatial derivatives, they only act on the basis functions themselves, for which you know the actual derivatives analytically. You don't need to solve or approximate them in any way. You can just write down the spatial derivatives here, which means you can compute your spatial derivatives exactly with no loss of numerical accuracy, right? So this is in contrast with, for example, finite difference schemes, where you represent the field at every point in space and evolve every point in space independently forward in time. In that scheme, to compute spatial derivatives, so this x-axis is one spatial dimension, you will need to do some polynomial approximation of the field locally and then calculate the spatial derivative and so on. So this is the the sort of the basis which makes spectral methods quite attractive to use for certain problems. Now, for the binary black hole problem, the choice of, as I said, the choice of basis functions is very important, and so is the choice of how we grid up the spatial domain that we will evolve in, right? So, let's look at the following snapshots of our grid. This here shows the grid as it looks near either of the two black holes. So, the singularity is inside this innermost empty shell over here, and outside the shell we have concentric spherical subdomains. Okay? And this stack of spheres is represented by this blob here as well as this sphere here for the two black holes, and in between them we have some truncated cones, cone-like subdomains that we use. As we zoom out further, we have these truncated sphere-like domains in this sort of intermediate region, which is a strong field region. And when we have gone far enough away from the two black holes, then we use simply spherical domains again. So this figure here shows the entire simulation domain that we use for evolving the two-body problem here. Okay? And the basis functions that we use in each of these shapes depends on the topology of that domain. Okay. So now solving for initial data, so will require, for example, knowing the extrinsic curvature tensor and the spatial metric tensor at one moment of time, which we can then use to evolve forward in time, right? So what we have are 4 constraint equations. The rest of the degrees of freedom we are free to provide arbitrarily in some sense. So we can use a the common, or at least the historically the choice that came about first and proved to be quite good was the conformal thin sandwich formulation, in which the metric is expressed in the form of conformal 3 metric, the conformal factor, the extrinsic curvature, and so on. And free data was provided for these variables, whereas the constraint equations were solved for the following variables, which include lapse shift and the conformal factor. And the boundary conditions on these variables at the 3 boundaries. So we have 3 boundaries, remember? 2 boundaries around the singularities and 1 boundary at the exterior end of our domain. So at the 3 boundaries, the boundary conditions we provide give us the relevant angular momentum in the system. The shift vector field that we provide at the outermost boundary gives us the orbital motion of the system in terms of the coordinates you're using. The shift vector field you provide at the inner boundaries outside the singularities but inside the horizons give us the spin on those horizons and so on. Okay? So, and then we solve the 4 constraint equations to get the full set of extrinsic curvature, which we will not go into. We can always chat about this later if you're interested. Now I wanted to get into how we do evolution and so on. So let's look at the evolution equations in a slightly more abstract form. So this is, say, the principal part of any first order set of hyperbolic PDEs. You have the time derivative on a set of fields and a coefficient matrix acting on the spatial derivatives equal to some source terms. Right? And for us, the set of fields are the metric, its time derivative and spatial derivatives, and these are all free variables now. The principal parts of the equations can be written down as these, and these are subject to constraint equations, gauge constraint and the definition constraint for this variable. So CIAB is equal to phi IAB minus del IGAB. Because we are evolving phi independently, there is no guarantee that it should always be equal to the spatial derivatives of the metric, which we are also evolving independently of phi. So we have to make sure this equality remains satisfied, and this becomes a constraint that must be obeyed during the evolution, right? But unfortunately, if you write down the evolution equations of these constraints, you find that they have a term that depends on the constraint on the right hand sides, which is what guarantees an exponential instability of this form. So I'll exemplify this with a much simpler example because I'm seeing a lot of puzzle faces. Okay, so let's look at the scalar wave system in flat space-time, right? This is second order form, first order form. Pi is the time derivative of psi, and phi I is the spatial derivatives of psi. So instead of one, we have these three set of equations that we have to solve, right? Now the constraint equations here are only this definition constraint, that this must always be obeyed throughout the evolution of these three equations. And if we write down the evolution equations for this constraint, it's not as bad as Einstein's equations, it's just equal to 0. But this also means that if due to some reason you introduce a numerical violation of Ci equal to 0, that violation will not decay back to 0. It will remain in your solution. It will remain forever, no matter how long you evolve the scalar field. Okay? So how can we cure this? We magically insert this term right here, which is just a multiple of the constraint equation itself. Analytically, since this is identically 0, I have not changed the original set of equations. So what I have done is in the space of solutions for psi, the physical solutions of psi have now become an attractor. Any deviation from the physical solution will lead back to the physical solution over time. How? If with this modification now you write down the evolution equation for the constraint, this is the form of that. And solving it is trivial. You find that constraint violation at any finite time will be exponentially damped compared to the constraint violation at the initial time. So this is a much more numerically stable form of the scalar wave set of equations. And so this is called constraint damping, for example. Okay? And this is also used in Einstein's equations. The red terms here are the constraint damping terms that we have included. For example, this term is analytically 0, right? Because this equal to 0 is our gauge condition. But inserting it changes the nature of the solutions for psi, pi, and phi. In that, the solutions now become attractors. Any deviations from the physical solution is unstable. It comes back to the physical solution space. And in fact, now you can control even the time scales at which any numerical errors decay away. Okay? Excellent. So now how do we deal with inequalities? Well, we avoid them. We try to avoid them. We just remove them from our domain. As you saw from the domain decomposition, the innermost shell that we put, innermost sphere that we put is right inside the horizon of each of the black holes. But that's about it. Just being inside the horizon allows us to not need any boundary conditions to be put during the evolution, because there will not be any incoming fields from this surface, right? Because all the fields will go into this and not enter our domain outside, right? So this technique is called excision. The other technique that I am not described here is called a moving puncture approach, where you allow the singularity to just move around in your domain, and if it makes contact with any grid point, you delete that grid point, and then you take one more time step till the singularity moves away from that grid point, and you do a local interpolation to get the value of all your fields at that grid point. So you delete it when the singularity touches that grid point, and you insert it back sometime later. That's the moving puncture approach, which we don't use. We use this excision technique. So this is more complicated in terms of how you have to handle the computational domains around the black holes. Okay. So, okay. So how do we make sure that our simulations are stable for long times, and our simulation technique adapts to the needs of the problem on its own dynamically? One key ingredient in doing that is something called adaptive mesh refinement. What does it mean? As the two black holes move from being very far apart to being much closer to each other, we can naturally expect the requirement for resolving the space-time fields to increase. We should need a lot more grid points as the space-time is more dynamical. In other words, our mesh must be refined as the system enters into a stronger and stronger gravity regime. And this is the purpose of having an adaptive mesh refinement, right? And our mesh density, or the number of grid points within each of the subdomains, is dynamically calculated based on the need for the problem, or need for resolving every field in your problem, right? So for example, this shows a typical sort of power in the spectrum. Okay, so let's take the space-time matrix. Let's take this time-time component, GTT, right? GTT we can expand in a spectral basis. Typically, if your basis functions are well chosen, the coefficients of the expansion look like this. They decay exponentially. If your basis functions, of course, are not well chosen, this will not be exponential. This may be flat or, polynomial like. But if it is well chosen, adapted to the shape of the field itself, how GTT actually looks, then you will get very quick resolution in a matter of very small number of basis functions being used to resolve that, right? So if we take, for example, only the first 6 coefficients to express GTT, then the error in representing GTT is given by the value of the last coefficient basically, right? And this is called the truncation error. So at all times during the evolution, we monitor the truncation error in GTT, GTX, TY, TZ, and all components of the metric, all components of pi, the time derivative of the metric, all components of phi, the spatial derivative of the metric, which is 50 variables. And depending on the truncation error rising in some components, we decide how many grid points to attach to that particular region of space and time. Okay? So this is how it is done in practice. For example, this x-axis is now evolution time, right? So let's not look at the whole graph, let's look at only one vertical slice of it, right? So this I think actually corresponds to GTT for a binary black hole problem. Let's look at one vertical line over here. These are the values of the various spectral coefficients, and you notice on a log scale they are almost uniformly separated, showing exponential convergence, right? Each coefficient is smaller and smaller and smaller than the previous coefficient. Now, we measure the truncation error, which is basically the magnitude of the smallest coefficient over here, or the highest order coefficient, right? And as soon as the measured truncation error is about to overshoot a target error, we add a new coefficient. So this pink curve didn't exist before, right? And then the error in representation goes down. It increases, and then we add one more basis function or one more grid point. For example, the yellow grid point here is just appearing out of nowhere, and this drops the truncation error over here. So this is how we, in real time, make sure that our grids are able to resolve the fields we are solving for, right? Without having to do it humanly. And another thing you'll notice is that the need for better and better resolution increases closer to merger. So this vertical line shows where the plunge begins of the two objects, and then you need a lot more coefficients very close to merger. The end here is actually when the two black holes just about merge. Okay, so yeah, let's not talk about that. Okay, and we need to track the black hole apparent horizons constantly during our simulations. We do so by, again, representing the shape of the horizon in spherical harmonics. In the initial data, we will solve this entire equation equal to apparent horizon. The definition, mathematical definition of apparent horizon, we'll solve for RLMs, the coefficients. But as we go forward, we will only update the coefficients. We don't need to solve the whole equation. Or in other words, we only solve for the deformations of the horizon given the horizon at the previous time step, right? So this is called tracking of the apparent horizon, and this is achieved using feedback loop control of these RLM coefficients. How am I doing on time?
We have 7 minutes.
Okay, good. So let's look at, okay, yes. the tracking mechanism is not different for spinning or non-spinning black holes. The number of basis functions you would need to describe the horizon is different. You will need, say, 30 and above YLMs to describe a rapidly spinning horizon. Whereas for a mildly spinning or non-spinning horizon, you might get away with 5 or 10. But the mechanism remains the same. You express the shape of the horizon in terms of a spherical harmonic basis, and you update the coefficients of that expansion. By the way, I've used the word horizon often in the last an hour or so. What we mean here is an apparent horizon, not the event horizon. Event horizons are global teleological concepts. They cannot easily be incorporated in numerical simulations. Apparent horizons are, however, local, quasi-local concepts. The way you define an apparent horizon is to take a congruence or a tube of photons, and you look for the divergence of that tube as time moves on. Okay, this divergence should be positive outside the horizon and negative inside the apparent horizon. So we look for the roots of this divergence, and that is exactly the equation we solve to get the shape of the horizon. We solve for a surface where the divergence of this tube of null rays is exactly 0.
So in older simulations like Chopwick's paper on critical collapse, they take the criteria that the labs go into zero as the indicator that the horizon has come. So is that cruder or is that in any way less efficient than this approach?
That is right. So they use a form of evolution equations where labs will go to 0 at the horizon. So labs going to 0 is actually an indicator of the presence of a horizon. In this, we have a different paradigm entirely. Horizons are present from the beginning. So we cannot use the formulation of Einstein's equations they used, because our labs will then be all the time 0 at the horizons. We have to use horizon penetrating coordinates, which have finite values of labs and so on. So yeah, because we are not looking for appearance of horizons, we already have horizons in our problem. Also, the moment of merger actually is defined by the appearance of horizons. So what happens is you actually don't see the two horizons make contact. What happens is a common horizon automatically appears outside both of them. So a common horizon will appear that envelops the two individual horizons, and the first moment it appears at corresponds approximately to the time of merger. And there's a whole field of dynamical horizons which studies the dynamics of these apparent horizons, and it can be used to describe the dynamics of the individual apparent horizons even after the outer apparent horizon has appeared, and so on and so forth. Okay.
You also said that some smoothness is guaranteed in case there is no matter.
Yes. Yeah. There'll be.
Is also used for say binary neutron stars.
Yes.
There,
So there. So the question is, the use of spectral methods with spec assumes some smoothness in the fields that we are solving for. Then how do we use spec for binary neutron star simulations? Right? For example, what do we mean by that? Is, for example, when the neutron stars make contact, there is bound to be a shock front that forms at the surface of the stars. How will we resolve it? We cannot. The answer is we cannot. So to do binary neutron star simulations, what spec does is have two grids. There is a spectral grid that is in the whole domain. There is a finite difference grid only in the local neighborhood and the interior of the neutron stars. So a big spectral grid and two small finite difference grids. These finite difference grids are the grids on which we solve the GR-MHD equations, or rather the MHD equations given the GR as input, and GR equations are solved on the global spectral grid, and the two domains, they talk to each other at every time. So you solve for Einstein's basically the metric and so on the spectral grid. You tell the finite difference grid, here is the metric at this moment of time. Now please evolve the MHD equations. It does so, and it gives back the right hand side of Einstein's equations, which feeds back into solving for GRB. It is very inefficient. And in fact, there's a new code that we have developed, which I will talk about tomorrow, which will go beyond the spec code in these fundamental ways, in fundamental ways to fix these kind of problems that we have. So, okay. So I think this is a natural time place for me to stop. I can speak about some results and the next steps in numerical relativity that we are working on in the lecture tomorrow. So thank you.